Hello, everybody, and welcome. I'm so glad when I get to talk to you. That means I'm got all my work done for the day, so I'm really excited. I hope you guys had a good weekend. Let's see. I had some Maritozzi. I had some really good Italian pastry. I live in a town that's like 500 people. There's not much going on, and stuff isn't always open. But there's a little. It looks like a house. Like there's like a porch you can walk up. But they have like it's a new place in town, and they have like Italian food. And it's really good. And they have really good pizza, and I got a Maritozzi, which is like it's basically like a big cream puff. So that was really good. So I hope you had a good weekend, and just had fun. It's really snowy out here. Got lots of snow, so I'm staying inside. Okay, so I wanted to share with you what I got for today. Again, thanks for subscribing and stuff, you guys. It's like so exciting to see like so many new subscribers and stuff like that. I'm having the time of my life. I don't know if you could tell, but like doing this and waking up and like sharing it immediately is like I'm really having the time of my life. Okay, so let's look at these slides. Okay, so first thing I did was I inserted like I said, there's an ad break for chapter 3, part 3 of the Set Theory Guide for Artists. And so I just put that in there because if someone says, what's an elementary embedding? I guess I would say an elementary embedding sort of preserves truth through J. So if phi of A is true in the bigger universe, then phi of J of A is going to be true in the smaller universe. Okay, so there's like a schematic. So there's like an image of that. I feel like when someone says what's an elementary embedding, this is probably just my own fault. But like someone says what's an elementary embedding, it's kind of saying like what's a car or something like that, where it's like it make go or something. It's like it's almost like to me it's like I want to describe the whole process of like how do you make an ultra power embedding to just say what it is. So okay. So also I was going to show like when you do this ultra power embedding, the first thing you do is the what is that? There's the diagonal embedding. I don't know, and I don't know if I used it in the paper. I used this like triangle. I don't know. I don't think that's like the normal way to do it. But for every A and V, C sub A is like the constant function with the value A. So it's like A forever, and then you collect all the things that are like it or are similar enough to it in a big enough set and in a big enough number of spots according to the ultra filter. So you make this thing and then you collect. Okay. But the thing is, and you can see in the picture, like in the ultra power, things look a little weird because it's not necessarily a transitive place, which is what we're used to. Okay, and so everything looks like a little weird, a little off, and then you take the Mostowski collapse. So we get back to a transitive universe. So that's the whole process. You take the diagonal embedding, or maybe there's another word for it. You take the universe, you get the ultra power, take the canonical embedding, and then you take an isomorphism from the ultra power to the final like I guess inner model or like the final like model. Which is transitive. Okay, so then after we take the Mostowski collapse, things are back to normal. Okay, also along the way we do this thing called Scott's trick, so that we're not dealing with like classes, we're dealing with like sets, and I think that's back to the diagonal embedding. Okay, and then the producers of the universe are all happy, and they say M, and then they had this weird kind of paradox kind of thing. M is a subset of V, but on the other hand, V is isomorphic to J of V, which is like a subset of M. So like M is sort of like a subset of the universe, but it's also bigger than the universe. This nice, like, kind of seemingly paradox. Okay, so the producers of the universe have had the main thing is that like triangle time commutative diagrams, and I don't know why I didn't put the little composition. I was like being cool or something, but it's like a J is you take the you take like the diagonal embedding followed by the collapse. So it's a composition of those two. Okay, so that's just like an insert for what's elementary embedding. Okay. All right, guys. So then let me see if I can. Okay, so then the next slide, I'll indicate to myself, put the next slide up. The next slide, I'm looking at my phone here. So the next slide is just like the slide for when I walk into the conference and it's like on the board and I'm like waiting at the front and I'm like, okay, just waiting. Yeah. Oh, maybe I see someone I know. Okay. They're talking to someone. Okay. Okay. So this is Mitchell Rank for Super Compactness and Aaron Carmody, February 18th, 2026. That's when I'm going to give the talk. It's at night. It's the ASL APA meeting, so Association for Symbolic Logic and American Philosophical Association joint meeting in Chicago. Yeah, in my book, if you know, I'm taking a break from the book to work on this, but in the book, she's like taking a break because the girl in the future, because she like got a note from the philosophy club. But I applied to give this talk, but it is actually on February 18th, which it could have been any day really, but I put that in my stories, February 18th, and then I got the notice, oh, you're actually talking on February 18th, so that's very cool. That's it. Okay, so that's just standing there. Oh, another thing I would say at the beginning, maybe I might mention, like, I was just thinking, like, while I'm waiting there, I might mention, like, you know, this it's sort of like when I applied to give a talk here, I didn't really know it was like a philosophy conference. I just was like, I just thought ASL, and I was like, oh, that sounds good. I've been to a lot of those meetings and stuff, and but it's like, this is a very mathematical talk. There's like induction. We've got these commutative diagrams. What else we've got? You've got embeddings. We've got filters. You know, it's very like mathematical. It's very like, if you just saw all the details and stuff, it's like very mathematical. So what's it doing in a philosophy conference? But that's the thing about set theory, is that it just bumps up against philosophy the whole time, because all of these like large cardinals are like they're like, we get these results through forcing, and these are like, the fact that they exist, these are like independent statements, large cardinal statements. So it's all like sort of right against philosophy. And so this is a very mathematical talk, but it's also like a very philosophical talk by nature, because I'm not a philosopher. I have read Sophie's World and I really liked it, you know, but that's about the extent. So except for what I've heard about from set theory, and of course, you know, hear people talking about, and there's like a lot of people at that intersection. So I'll be really happy to go to this talk and like, you know, meet other people that are at that intersection. But that's the nature of set theory. Okay, next slide. Okay, so this slide is, this will be somewhere in the beginning, and this is just like talking about this theme of killing them softly, which is like this idea that we're gonna kill the degrees of large cardinals. This whole talk and on my thesis is all about like, how do degrees of large cardinals and forcing interact with each other, and they like interact perfectly with each other, and it's like, what is going on? So if you want to ask a bigger philosophical question, like, what is going on? Why does degrees of large cardinals and forcing just fit so nicely together? And so this is just, this is like destruction and creation, some other killing them softly results, and these are already existed before I wrote my thesis and stuff. These are, so I'm saying like that this like destruction and creation is a big theme in set theory regarding large cardinals and forcing. Okay, so these are some theorems. Shanker, if kappa is weakly measurable, then the measurability of kappa can be destroyed while preserving that kappa is weakly measurable. So you can get the idea of the theme of this. I'm going to be doing this with super compact cardinals, and I'm also going to show measurable cardinals. And I might mention inaccessible and Malo also at the beginning. Okay. Let's keep it going. Okay, then we have this theorem by Gitman. I think Gitman had like the preservation part, and maybe I did like a little destruction part or something like that. But I just give this, and this is like Gitman's theorem. If kappa is strongly Ramsey, then there is a forcing extension where kappa is not weakly measurable, but is still strongly Ramsey. Okay, I think I just like used her result and like sort of phrased it in that way to make it more like a destruction preservation. Oh, I'm thinking of an I Heart Huckabee destruction, creation, destruction. Exactly. Theorem Gitman, if kappa is strongly Ramsey and ineffable, then there's a forcing extension where kappa is not ineffable, but it is still strongly Ramsey. And this is like, again, this is like, they had like most of the theorem. I just phrased it. This is Hampkins and Cholat. And this is, if kappa is a theta super compact, then there's a forcing extension where kappa is theta super compact, but not theta plus super compact. And so this already, you might think, there's already like degrees of super compact cardinals right there. There's like levels of super compact cardinals already right there, and we can already softly kill them. But there's even more. Like you can be theta super compact and have rank 2 or rank 5 or whatever, or rank kappa plus or something. Okay. And finally, Magador's theorem, and there's more. If kappa is strongly compact, then there's a forcing extension where kappa is strongly compact but not super compact. Okay, so we're like using forcing to distinguish between large cardinals. Okay, you guys, I'm getting to the end. I want to make sure this is like, 5 to 10 minutes. So thanks so much for stopping by once again. I'll see you tomorrow. So I'm not going to like miss you that much. I'm going to see you tomorrow. So have a great day.